Okay, so I'm Nunzia Gallo. I'm assistant professor at the University of Salento, and I have 10 years of experience about biomaterials for regenerative medicine application. And it's a very pleasure for me to moderate this young scholar forum. But let's say something about our journal. Our journal has an initial target impact factor higher than 5 and would be ranked as a Q1 journal. The frequency of publication is quarterly and it has a single blind and rigorous peer review process. There will be no APC before 2029. And is included a free English language editing. The journal organizes also annual Best Paper Awards and Frontiers Forum and Scholars Interview. To discover the latest research and stay updated with our journal news and submission opportunities, please follow our LinkedIn, X, WeChat profiles. But what are the scopes of our journal? BME Horizon is a peer-reviewed open access journal that provides an international platform for publishing high-quality research and innovative advances in biomedical engineering, biomaterials, regenerative medicine, medical devices, drug delivery, and related interdisciplinary fields. So we welcome various types of high-quality submissions, including articles, review, or perspectives. Subjective area includes, but are not limited to, synthetic biology and biotechnology, regenerative medicine, biomechanics and rehabilitation engineering, biomedical imaging and diagnostic, medical devices and instrumentation, bioinformatics and computational biology, nanotechnology in medicine, sustainable biomedical solutions, and biomaterials and tissue engineering. And here there are some links where you can find our home page and the link for the submission of your article or your contribution that obviously is more than welcome. And in this slide, we would like only to show you our editorial board with our editor-in-chief, that is Byung Ma, our executive editors that are Xiaodong Xu and Kong Xu, associate editor, and the other editorial board members. Our journal currently has 4 special issues that are open for submission. Maybe one is closed, that is on 3D bioprinting and biomaterials, but there is one special issue that is still open, that is metal-based composites for biomedical functional application. As regards academic activities, our journal organized a symposium on mechanobiology across the tree of life that has been held both in presence and virtual in June by Prof. Kim Hwan of the Department of Bioscience and Biotechnology. And now I think we can start with the first presentation, the second one, I suppose, because, okay, of Professor Xiaozhang Wang on musculoskeletal tissue science and tissue regeneration.
Can you see me?
Yes, I can see your presentation.
Okay. Dear respected experts, good morning or good afternoon. I'm Luo Yang from the first affiliate hospital of Ningbo University, and also a young editor board member of BME Horizon. It is my great honor to present our research work, 3D bioprinting tissue and organ constructs. From structural mimicry to functional validation. 3D bioprinting enables precise arrangement of biomaterials and cells according to pre-designed shapes and holds the great application potential in tissue repair, organ regeneration, and disease model construction. In this presentation, I will introduce the embedded suspension bioprinting technology developed by our team, and as well as its applications in fabricating smooth muscle, skin, corneal, and vesicular tissue. Conventional extraction-based bioprinting requires high concentration bioink to maintain structural, geometrical, and after printing. However, high concentration biomaterials had nutrition exchange and cell growth. Meanwhile, higher extraction pressure is required during printing, which may easily damage living cells. As a result, there exists an inherent conflict between printing performance and cell reliability. To address this issue, we adopted embedded bioprinting, where printing is performed inside a gel supporting medium. The extruded printing structures are instantly supported by the solid gel to avoid color pass and deformation caused by gravity. Even soft, low viscosity bioink can be used to fabricate complete three-dimensional structures. A high-performance supporting gel possesses three key properties: yield stress, shear thin, and safe healing behavior. When the printing nose moves, the gel falls under shear force. After the nose moves away, the gel quickly returns to a solid state to fix printed fibers. This reversible solid flow solid transition ensures a smooth printing process. Based on the above principles, our team developed a collagen-based suspension supporting gel. Collagen can form hydrogels under specific island conditions. We first prepared one hydrogel and then process it into microgel particles. At rest, these microparticles are densely packed to support printed constructs. Under printing-induced shear force, particles slid against one another to enable printing. Once external force disappears, particles lunge to restore supporting capacity. Experiments confirm the uniform particle size, reliable shear thin, and self-healing performance, which fully satisfies the requirement for embedded bioprinting. We further evaluated the printing accuracy and cell compatibility of this medium. Curved structures, suspended architectures, inner cavity, and various tissue models were successfully printed. The printed samples faithfully reproduce designed morphologies with tight internal layer binding and no ambiguous calipers. Compared with conventional in-eye printing, this technology greatly reduces gravity-caused structure defects and is especially suitable for fabricating complex external structures and suspended constructs. Cell loaded bioprinting experiments demonstrate high post-printing cell viability. Cell can normally spread in suspensive country. It proves that our system can achieve high resolution shaping as well as fabricated bioactive tissue models. Using this technology, we first fabricate oriented smooth muscle tissue. Smooth muscle is widely distributed in blood vessel, bladders, uterus, and the digestive tract. The orientation of cell arrangement directly determines the contractile function of tissues. Directional scaffolds were prepared via embedded bioprinting to guide smooth muscle cells to align orderly along printing paths. Cell irrigate along the printing trajectories and form containers, well-organized tissues. Animal experiments show that such smooth muscle constructs effectively promote the repair of the muscle defects. Next is the fabrication of biomimetic skin. Native skin mainly consists of epidermis and dermis. We adopt layer by layer bioprinting to deposit epidermis cells and dermis cells into their respective regions. Staining results reveal a distinct bilayer skin structure. Immunofluorescence layer proteins are located in the lower epidermis, while keratin-associated proteins concentrated on the superficial layer, consist with the differential features of native skin. In animal skin defect models, printing skin effectively accelerates wound closure and tissue reconstruction, exhibiting favorable in vivo repair effects. Thirdly, we fabricate three-layer biometric kernel. Native kernel is composed of the epithelium, stroma, and endothelium, each with unique circular components and physiological functions. We mix the different kernel cells into Boink and performed step-by-step bioprinting to construct a tri-layer kernel architecture. After printing, cells in each layer remain visible and gradually develop corresponding tissue morphology. Staining verifies the expression of layer-specific signature proteins. The printed kernel not only replicates the macroscopic three-layer anatomy, but also realizes layer-specific features at the molecular level. In follow-up studies, we will further evaluate light transmittance and long-term in vivo stability. Finally, we constructed multi-layered biomimetic blood vessels. Native blood vessels are far than simple hollow tubes. They are complex structures composed with endothelial cells and smooth muscle cells. Combining pre-stressed assist printing, surface coating, and cell seeding techniques, we successfully fabricated multi-layer vesicle constructs. Fluorescence shows smooth muscle cells listed in the outer layer, and the endothelial cells full cover the luminal surface, closely mimicking native blood vessel architecture. During culture, outer smooth muscle cells spread fully, while the inner endothelials fuse with each other to form an intact luminal lining. This dual cell model recapitulates with the layered structure of native blood vessel and can apply to access vessel contraction, biliary function, and blood compatibility. In summary, the supporting gel we developed integrates yet sharing and safe healing properties, providing a stable environment for providing soft hydrogel and complex three-dimensional tissues. Nowadays, 3D bioprinting has moved beyond the simple structure formation towards precise regulation of cell alignment, tissue stratification, and biological functions. It shows broader prospects in tissue repair, organ regeneration, disease modeling, and drug screening. This concludes my presentation. Thank you for your attention.
Can you hear me? Sorry.
Yeah, we can hear you.
Okay. Good afternoon, everyone. This is Xiaozhao Wang from Zhejiang University, Liangzhu Lab. I would like to thank the organizer to inviting me to this forum. And today, I would like to share our recent efforts in understanding the material science of human musculoskeletal tissues, especially with the particular focus on the multi-skill software interfaces for the next generation regenerative medicine. And our group leader is Professor Hongwei Ouyang. And why the interfaces matters? And in engineering material, the interfaces are often considered and the weak points during because of the stress concentration. However, in nature, multiple interfaces exist. Well, it have very extraordinary functions like the mechanical integration, the energy dissipation, the functional adaptation. So the key question becomes, what are the structure and the material principle that make the biological interfaces in nature so robust? So Nature is a master engineer. It provides a lot of examples of the composite material design, like the multiple software interfaces in human bodies and some other kinds of life. The biological structures achieve remarkable mechanical performance through the sophisticated hierarchical designs. So the decoding these natural structures or the strategies could provide a blueprint for the designing the next generation of designing advanced biomaterials. And based on this concept, we focus on the human musculoskeletal system, especially for the knee joint, because the knee joint represents excellent interface model systems. It contains multiple complex interfaces like the soft-to-hard interface, osteochondral interface, the ACL to femoral or to tibia enthyses, and the meniscus root to bone interfaces. So this interface have very superior mechanical environments, and like the anti-fatigue adhesion property, the superior force transfer property, the good toughness and high strength. The underlying fundamental mechanism is very interesting and need us to further study. We first focus on the meniscus root to bone interface. This is a very good natural fatigue resistant model. This meniscus could transfer complex mechanical loads where the bone provides structural support, and this complex structure could maintain the joint homeostasis. And a good question is why the interface between the meniscus root and the bone could survive long-term sac-like loading. And the structure and the composition basis and the toughening mechanism of this interface is still not clear. So next we are using multiple material science technology and also the biomechanics techniques to investigate this gap. We found during the past year, the excellent mechanical properties of different materials or tissues were originated from the multi-scale structures at different length scales. These structures have different energy dissipation properties, and this provides a very important design principle for us to investigate our meniscus to bone soft-to-hard interface. So we first characterize the superior mechanical properties of this interface, and we found the meniscus to bone interface exhibits excellent fatigue resistance adhesion properties, good toughness, and also the adhesion properties. And also we using AFM to evaluate the mechanical intrinsic modulus transition, and we found this transition show exponential increment. Using FEA simulation, we found such exponential increment of the modulus had the or minimize the stress concentration and allow efficient force transformation. So these results highlights a key principle: gradient structure or gradient modulus transition is very efficient for the integration of the mechanically mismatched tissues. So next, we investigate the structure changes at the graded mineralization interface, and we found also use FIB-SEM, also the AFM. We found the minerals at the soft-hard interface across over 30 microns, show a gradient change of mineral morphology and spatial distribution. And then we investigate the composition of such calcium phosphate minerals composition, and we found the minerals undergo a phase transformation from the amorphous calcium phosphate to immature hydroxyapatite, we called HAP, and finally show the very mature HAP, especially had the lacy-like structures of the mature hydroxyapatite nanoscale structures. And such dynamic mineral transitions, including the composition of the structures, could provide a mechanism for controlling the mechanical properties during tissue interfaces. And also we use Raman, SRS, and cryo-EM and EOS to examine the mineral composition, the crystallinity, and also the chemical environment of these minerals. And we found gradient changes in terms of the composition, the crystallinity, and the chemical environment could be observed across the soft-hard interface. And next, we use LC-MS to examine the biomolecules enriched at this interface. And we found the enriched biomolecules is very important in regulating mineral maturation. And the way, especially we found the MGP protein, which could act as important ACP stabilizer at the interface to maintain the dynamic balance between the unmineralized and mineralized tissue. Also, we examined the function of this protein in vitro using TEM. And this provides inspiration for designing biomimetic mineralization materials for future design. Also, we investigate how the molecular components contribute to the adhesion property of the interface. And AFM adhesion force map revealed the enhanced adhesion regions correlate with the interface enriched aggregates. And this suggests that the mechanical properties of the interface is generated through the cooperation of the mineral phase, the protein like collagen matrix, and also the aggregate molecules like proteoglycans and also some other kinds of molecules. So the function emerges from the multiple interaction of these complex molecules. So next, we are very curious about how the physical origin of the high mechanical performance and crack resting dynamic and the soft-hard interface. And so we fabricate custom-made in situ device to to study the in situ mechanical response of the tissues using confocal microscope. And also at nanoscale, we collaborate with Professor Ze Zhang from Zhejiang University, and using their in situ SEM tensile test, we study the in situ mechanical response of the minerals, especially the unmature calcium phosphate minerals and the collagen fibrils and the tensile force. And also we also use FE simulation to study the collagen fibril and the mineral responses to the force when under the tensile stress. And we calculate the molecule, the modulus ratio of the reinforcing hard face to the soft face and the soft at the soft to hard interface. And we found across the soft to hard interface, the modulus ratio were gradually increased. And when the ratio increased, the energy dissipation property or the capacity could be enhanced. So these complex structures and modulars distribution could provide the interface very complicated mechanical performance and to maintain the joint homeostasis. And then we investigate or examine the mineral the native mineral phase is very important for the mechanical properties of the interface. So we over mineralized or demineralized the interface, and we found such treatment could result in reduced toughness and the strength of the interface. So this means the very complicated mineral structures and distribution, and also the soft molecules is very important for the toughing mechanism of the interface. And also we conclude these multi-scale toughing mechanism at the soft to hard interface at the figure shows. And at tissue levels, the mechanical load is initially accompanied by the soft ligament tissue through the fiber sliding, or the strengthening, or the collagen deformation. It could allow the adaptive response of the interface to prevent failure. And at the macro scale, the metastable or of the immature minerals or collagen could undergo the sliding or rotation. It could dissipating energies through frictional interactions. And at a nanoscale or molecular scale, the reversible molecular bond could break or reform between the immature minerals and the soft matrix. And so this superior toughness of the soft to hard interface could achieved by the multi-scale structure reinforced mechanisms. And we conclude also we after understanding the mechanism, we also translate these principles into high performance materials. So we found the SAP to HAP transition codes enhance the adhesion performance of the molecule-based hydrogels. And also we synthesize scaffolds, and we found SAP to HAP transition could promote the strength of the soft to hard composite scaffolds. Therefore, the biological mineralization mechanism can provide new blueprint for the next generation of high-performance biomaterials. We conclude this study using this video. And the key message from this study is a 30-micron software interface contains sophisticated gradient mineralization structures and the tapping mechanisms. Although the interface is very, very small, but it determines the overall function of these structures. So it also provides a blueprint for future interface design.
Minerals slide to dissipate energy through friction and molecular bonds breaking. These mechanisms toughen the structure, ensuring normal knee function.
Also, the next example is the ACL to bone interface. ACL is very important for our human knee joint. It's very important for the knee homeostasis. So, although the ACL is a single ligament, but it have two attachment regions to femora and tibia bones. And these two interfaces require different mechanical properties. So in these studies, we found that the distinct regional structures and compositions could enable functional adaptation to different mechanical loading conditions at the two different interfaces. And the next example is the osteochondral interface tissue. This osteochondral interface tissue called connected cartilage and bone. And in this study, we found the multi-scale structural assemblies, the exponential modulus profile, and the nanoscale hydroxyapatite structures, and also the biomolecule enrichment and the interface together provide the interface superior force transformation properties. So understanding this interface is very important for future structure design for osteochondral interface regeneration. And the last example is the growth plate. The growth plate represents another biological engineering system. During the development, the growth plates could generate directional bone growth through precise spatial organization. So in this study, we are evaluating the physical and chemical niche between the software interface at the epiphysis to growth plate interface and metaphysis to growth plate interface. And we found that the nanoscale crystal assembly and regulatory mechanism at the two different interface is distinct, and such differences could provide the polarized bone elongation and mineralization of the interface tissue. And based on this mechanism, we also synthesize the uncontrolled stable ACP, we called calcium phosphate nanomaterials, and such nanomaterials could provide high performance for bone regeneration, especially in aging microenvironment. And lastly, we also study how the system could fail during the disease. We use OA as a disease model, and we evaluate the pathological calcification of cartilage tissue and osteochondral interface tissue process during OA development. And we found such pathological calcification could induce dysregulated the mechanical properties of the cartilage region, and such results will resulting in progressed OA development. And we think understanding this disease progression from the material science perspective could provide new therapeutic strategies for future OA disease treatment. This paper was reported by NSFC and also cited by different professors. Finally, our research group focused on understanding the material basis of human tissues. And today, we in our forum, I just introduced the material basis of the human tissues. And next step, we also develop the mimetic engineering strategies for the material design. And finally, using these biomaterials strategies, we achieve high performance tissue regeneration. So the ultimate goal is not only to investigate the material basis of human tissues. More importantly, we could provide new strategies for future tissue regeneration. Finally, I will thank Professor Ouyang and our collaborators, because these studies are the results of the interdisciplinary collaboration among researchers from the material science, the biomechanics, biology, and clinical medicine. I would like to thank our team leader, Professor Ouyang, and our collaborators and our PhD students, and also thank the funding for supporting our research. Thank you for your attention.
Now it's time to start our free discussion. All of us are free to share our question in the chat box. And if you would like to speak, raise your hand and I will invite you to speak. Please respect all viewpoints and avoid interrupting others. And now we can start. If there are any questions. Does anyone have some questions? Okay, maybe I can.
Yeah, I have a question. Hello.
Okay, good morning. Please.
Yes, my name is Dheeraj Bhatia. I'm a faculty in Biological Sciences and Engineering, India. First of all, a very good talk, like very, very impressive presentation. I had like one question, which is also kind of a bit general, like whenever we all work in different biomimetic approaches towards regeneration or tissue engineering, one fact or one challenge which we all face is the effect of these materials on the immune system when we go into the mouse models or any other animal studies. A lot of the time we do see inflammation response happening during the graft or during. So I just wanted to check if there has been any kind of efforts or suggestions where we could combine, like let us say, immune suppression or immune compromisation along with the materials for better animal studies or better grafting.
Yeah, the immune response is a very, very big issue. Yeah, immune suppression could be one choice. but also the use of biomaterials that are, for example, for the use of ACM components such as collagen, hyaluronic acid, can help in reducing the immune response of our system, because there are molecules that are recognized, or more than others, recognized as self.
Yes, yes, thank you. And also, sometimes, no, not sometimes, challenges also when we are not just making the biomaterials, we get like bacterial contamination. So, like sometimes what we do is like when you are even making the synthetic biomimetic systems, put some antibiotic as a combination to kind of avoid antibacterial growth or any infection during this thing.
Yeah. Infections are another very important issue.
Yeah.
Usually for biomaterials that should be used for biomedical engineering, so that are approved. In Italy, we have some. In Europe, and in Europe, we have some. We have the CA certification, the MDR. That are some regulations that in America, in USA, there is the FDA.
Yes.
So biomaterials for biomedical engineering should be safe, should be free from bacteria before use.
Yeah.
However, during the implantation could happen.
Yeah.
And avoiding bacterial contamination with the addition of some antibacterial agents, for example, of silver, is quite mandatory in our field.
Yeah. No, I get it. Yeah. Thank you so much. Yeah.
Nothing. Any questions? Okay, maybe I have one question for Professor Wang Lu on 3D bioprinting. I would like to ask about the choice of his biomaterials for the development of his 3D printed castrates. And I take this time to sorry for the incorrect pronunciation of your names.
Professor Luo. Luo老师.
Okay, maybe he's not hearing us now. But I have another question for Professor Xiaoyang Yang about her impressive research. I'd like to ask if she thinks that the scientific research is.
I'm sorry.
Don't worry.
Online.
Sorry for the incorrect pronunciation of your name.
I think biomaterial selections plays a role in the whole 3D bioprinting workflow. It determines printing performance, like lithological properties such as viscosity, yield stress, and shearing behavior affect the extruded ability, sharp fidelity, and post-printing structure stability. So I think biomaterial must be seal compatible, and selected materials must be non-cytotoxic and support the seal adhesion, spreading, proliferation, or differential. Yeah, and so on.
Okay, thank you. And what do you think about collagen and hyaluronic acid as bioinks? Since they are ECM components, maybe they can interact very well with cells. What do you think about?
Yeah, collagen and the ECM is the natural printing, and the cell we have the many good cell compatibility. So, but they have the they are soft, so it's difficult to build in the shapes.
Okay, thank you.
So it seems that there's no further questions at the moment. On behalf of the editorial office of BME Horizon, I would like to sincerely thank our host, Professor Gallo, for guiding today's session, and our speakers, Professor Yang Luo and Professor Xiaozhao Wang, for their excellent presentation and valuable insights. We would also like to thank everyone in the audience for joining us today and for your interest and participation. We hope that today's forum has provided you with a new perspective and stimulating ideas on the future of tissue engineering and regenerative medicine. Thank you again to all our speakers, our host, and everyone who joined us today. We look forward to seeing you again at our future forums and events. Have a wonderful day and goodbye, everyone.